presentation in our seminar on information diffusion on complex networks.
Thank you very much, Leif, and thanks to you and also to Andreas for setting this up. It's a strange period where there are very few seminars, so I think it's very nice to be able to meet our colleagues online and hear some of the latest developments. So I'm going to be talking about information diffusion on complex networks, and this actually means that I have to explain two things: information diffusion and complex networks. And I'll do this in several trials. I'll start with explaining what complex networks are, and then I will say something about various forms of information diffusion that we might be interested in. Okay. So complex networks in general are very large graphs, and therefore in mathematical terms we'll be thinking about taking limits to infinity. But they're also highly heterogeneous, and that actually means that the various vertices in these networks play rather different roles. So for example, on the right, you see the internet, and on the internet, you have the backbone routers, and they're much more important for internet traffic than sort of the average router that is present on the internet. On the left, you see yeast protein interaction networks, and also there, we actually know that there are some proteins that play a much more profound role in the biological function that these proteins have. And I think this is just a reality that we see in many of the real world networks, and that is that they are rather heterogeneous in their nature. Now, many of these networks come from various different origins, and we'll see some other examples again later on. So you might think that they have actually nothing in common, so why study them all simultaneously? But actually it turns out that many of these real-world complex networks have some unexpected commonality, and that's what we would like to be focusing upon. So one of the things that, that many of these networks share is, as I've said, that they're highly heterogeneous. And more particularly, if you look at the degree distribution of the various vertices in these networks, then as I said, this is highly heterogeneous, but also it seems that in many examples, this degree distribution actually follows a power law. And that's, of course, rather remarkable, because we know that power laws are very important because they are examples of probability distributions that have only a finite number of finite moments. And therefore, you can imagine that having one of these power laws means that you actually have a high amount of variability in the degree structure in these networks. And I've shown here two examples. The left example comes from the in degree of a crawl on the World Wide Web, and it's conjectured that the in degree has this power law behavior, and we certainly see a picture that looks very much like this. On the right, we see the degree distribution in internet, and as you can see, the degree distribution is much more smooth, and that's because the colleague who made this picture, Dima Kryukov, actually binned the picture in order to smoothen it out a bit. Now, we've drawn these pictures in a very particular style, and that's the kind of style that you will see in many of the applied papers on network science, and this is sometimes called a log-log plot. And the reason is that many of these pictures in a log-log plot start looking like a straight line. And a straight line, a perfect straight line, would mean that the proportion pk of vertices with degree k satisfies that pk is a constant times an inverse power of k. And as you can imagine, this, of course, decays when k tends to infinity, but it decays fairly slowly. So that actually means that in a very large network, you're still going to see vertices of actually pretty large degree. And that's exactly what you see in these two pictures. And even more astonishing, there are many claims that say that the empirical values of the power law exponent, that of course plays a very profound role, should be in between 2 and 3. There's a lot of discussion about whether this is the case or not, but if this were to be the case, tau being in between 2 and 3, if the pk would be a probability distribution, it actually means that the variance of the random variable that pk is the probability mass function of is infinite. And of course, we know that processes with infinite variance are rather peculiar, and we'll see that in more detail a bit later on. So this is one of the properties that many of these networks have. The second property is that these networks, even though they're extremely large, are rather small in the sense that sort of typical paths between pairs of vertices are relatively short. So here we describe the intrinsic or the graph distances between pairs of vertices. And what this means is that you pick a vertex and you pick another vertex, you assume that they're connected, and then you count sort of the minimum number of edges that you need in order to hop from the first vertex to the other vertex. Now, if you do this for all the different vertices in the graph and you put that in a nice histogram and you renormalize that histogram in such a way that you get a probability distribution, then you see pictures of the kind that I'm showing now. So the left again corresponds to the World Wide Web and the right corresponds to the Internet Movie Database from 2003. So what we see is that these graph distances are extremely small. They're much smaller than the size of the network. You should really think about the networks being of size several millions. And if you see distances of order 7 or 8, then this is very small compared to the size of the graph. And that's what is generally called the small world paradigm. And we see that many of these networks do satisfy this small world paradigm. And you should bear in mind that this really is different compared to the type of worlds that we're used to. I mean, if you're thinking about, let's say, a square on Z2, if you wanted to have n vertices, then actually it's a square of size square root of n by square root of n. And if you pick two vertices uniformly at random, then the graph distance between them will be of order the square root of the number of vertices in your network. So for example, in the Internet Movie Database, that would correspond to the square root of roughly 1,000,000 and therefore roughly 1,000. And you really see the distances are much, much, much smaller than this. So there's something special happening here. Now here's some material. I don't want to make too much advertisement, but if you want to know something about sort of real world application of networks, you might have a look at the network pages, and I'll show a demo a bit later on. Right. So that actually gave the very first explanation of what it means to be a complex network. I mean, we still need to think about how to model that mathematically, and that's what we'll do a bit later on. But let's first think about information diffusion and in particular about smallest weight problems. So in many applications, what you would like is you would like to move something from a source to a destination. This could be a gossip, it could be a virus, maybe you don't want to spread that, but or it could be an email message where you want to transfer a packet of information. And often in these settings, it takes a little bit of time or it takes a bit of cost in order for you to use a particular edge in your network and to transfer the message along. Certainly, if you're thinking about the gossip, it will take you some time to tell the gossip to any of your friends. So these are then called the traversal times. So if you want to know how this information is diffusing over the network, then you want to track as a function of time if where the information is located when it starts from a certain source in the network. And of course, the information is going to arrive at a certain destination by the path that actually minimizes the traversal times along the edges. So we immediately are led to smallest weight problems. Now, this is not the only thing that we're often interested in. We're sometimes also interested in the number of edges that are being used along this optimal path. So for example, in internet, this number of edges is a good measure for the amount of delay that you're experiencing for the traffic. But if we're thinking about traversing a rumor or a virus, then the number of edges that is being used also signifies how many intermediate people are either hearing the rumor or being infected. And that's certainly something that we would like to know about. So that actually gives rise to two problems, namely, what is the structure of the smallest weight of traversing information between source and destination, and also how many edges are involved in such a shortest weight path. Now, throughout this talk, we'll actually assume that these edge weights are IID random variables, and that means that there's actually double randomness in this problem, and problems with double randomness are particularly interesting. So here we have double randomness because of the randomness in the process, in particular the randomness in the edge weights, on the one hand. On the other hand, we will also be modeling our networks through random graphs, and therefore also the graph itself is random. And you actually want to know what the interplay is between these two sources of randomness. And I would like to say that we've been looking at small weight problems before, ultra small world properties. And of course, you should realize that you can also go back to the graph distances by just assuming that every edge has weight 1. So this is a particular instance of this smallest weight problem. All right, so here we're talking about information diffusion. And what you should bear in mind is that if you're actually putting IID traversal times on the edges, then what we're thinking about is a process that is sometimes called first passage percolation, which has attracted a lot of attention for first passage percolation on ZD. And here we're doing first passage percolation on a more general or heterogeneous network. Now, in particular, first passage percolation has attracted a lot of attention in the case where the edge weights are exponentially distributed. And the reason for that is that exponential distributions have the memoryless property, and therefore the whole growth process of who can be reached has a nice Markovian structure. That is actually particularly nice. But of course, in many real world systems, there's no reason whatsoever to assume that the traversal times along all of the edges are exponential distributions, and therefore will also be varying these edge traversal times. So we're looking at a rather general first passage percolation problem on a general network. So this is what I mean with information diffusion on a network. Now I would like to go back to my internet example that will actually feature throughout the talk. Of course, we can also think about diseases and how they spread, and I will spend some words on that a bit later on, but I have to warn you that I'm certainly not an expert in that field. But if we want to think about internet traffic, then clearly what we have is a problem where we're trying to send out a lot of information over the edges in a network. In this case, the edges of the network are the physical cables that exist between routers. And of course, it's not entirely obvious how this routing takes place. So that actually makes the problem somewhat difficult. But there is a little bit of literature about this. I mean, most of the routers in the true internet are actually produced by CISCO. And CISCO has recommendations for the link weights that actually do play a role in internet traffic. And the CISCO recommendation is that the proportion of link weights with a value at most B should be equal to the proportion of cables that have a certain capacity, at least 1/B. And here in capacity, you should really think about the bandwidth of the cables. So it really becomes very physical. And of course, we have no idea what the empirical properties are of the bandwidths of cables in internet, and therefore we'll just be assuming that these are IID distributions. Of course, this is certainly a simplification of the real world, because you can imagine that the bandwidths in the real physical internet cables have some dependencies. So the IID nature might actually not be particularly correct. But it's like with statistics. You start with the simplest possible case, and then you try to work from there. Now, this is a picture that has been inspiring us in order to look at this problem. And what this shows is what is sometimes called the Hopcount in internet. And this you can actually measure through a device which is called traceroute. And in traceroute, you send an email message from a certain source to a certain destination. And not only will you see that the message actually arrives at the destination, but you will also get all the IP addresses of the intermediary routers that have been used in order to send the traffic along from source to destination. So if you start sort of plotting how many of such intermediary routers are being used, you get a picture alike the one that we're currently seeing. And what you see is that these distances are quite a bit larger than the proper graph distances that you see in many networks. So there's some routing taking place in the internet that seems to be a bit different from graph distances. And what you also see is if you squeeze your eyes half shut, is that this actually looks a lot like a Gaussian distribution, or maybe a Poisson distribution. And in fact, what you can empirically observe here is that in this data set, the mean and the variance are not very far apart. So they're of an equal order of magnitude. So it really does look a lot like a Poisson distribution. So the question is, how could such a central limit theorem in such a data set arise? Can we find an appropriate model that might explain something like this? Okay, so the very general setting that we're going to be looking at is we're going to be looking at the smallest weight between two uniformly chosen vertices in a collection of n vertices in total, and we'll think about n as being very large, and in fact we'll be taking limits as n tends to infinity. And what we'll do is we'll choose our starting point and our destination as being typical, and therefore we'll choose them uniformly at random. But we will be assuming that they're connected, because otherwise, of course, no traffic can flow between the two. And then what we're interested in is what the minimal weight is of the path connecting the source to the destination. So the weight of a path is the sum of the edge weights in that path. That's actually the quantity that we see right over here. YE is the edge weight of edge E. And we're summing over all the edges that are in my path. So pi is a path that connects my starting point, which is denoted by U1, to my destination node, which is denoted by U2. So that's one thing that we're going to be very much interested in. And if we're talking about a rumor, this would describe the amount of time it takes for the rumor to spread from the source U1 to a random destination U2. But we're also interested in how many people are involved in sort of traversing this rumor, and that's what is called the Hopcount, and we'll denote that by HN, and that's the number of edges in the smallest weight path. And what we will be assuming is that our weights are continuous, and that has the nice feature that actually this minimal path will be unique. So we can actually talk about the number of edges in it. If you allow for distributions that are discrete, it might be that there are several paths of equal weight that connect source. If that is the case, then it's much harder to talk about the hop count, because they actually might have different number of edges in them. And of course, you can do this on a general graph. And as I said, first passage percolation has been investigated a lot on ZD.
Did we lose Remco?
Yeah, I think we've lost the speaker, yeah.
Okay, let's see if he finds us again quickly. Oh, and there he is.
Can you still hear me?
Now you're back.
Yeah, just about.
Something went wrong. I especially went down to sit in my living room where our internet is best, but still it's not particularly good. I don't know why. I'm hoping that nothing is going to happen now. Can you hear me well?
Very good now.
Yeah.
Very good. Okay. So this is where I was stopping. You can formulate this problem on a general graph. And what I would like to do now is I would like to restrict to a particular setting that has the same level of heterogeneity that you see in real world networks. And this is called the configuration model. And the nice thing about the configuration model is that it's a model in which you can vary the size of the network, the number of vertices in it, but you can also vary the degree structure in the network. So we're just going to be assuming that we have a setting where we know how many vertices we have, and we know what the number of neighbors is of each of these different vertices. And this is just what is given. So for example, you could obtain that from a data set of a real world network, and then you of course know how many vertices there are in the network, and you know how many neighbors each of the vertices has. Now, in some cases, it will be convenient to take these degrees to be IID. That's of course a very natural setting for probabilists, but we won't always be doing that. What we will be interested in is settings where these degrees obey power laws in the way that I've described in my scale-free paradigm, in order to be able to discuss the level of heterogeneity that is present in the models. What you should bear in mind is this heterogeneity is measured in terms of a parameter tau. It's a power law exponent, and the smaller tau is, the more heterogeneous the network is. Very large taus means more or less like all the describe yet what the model is. But what you should bear in mind is that each of these vertices now has a certain degree, and you think of little stubs as coming out of that vertex, and you pair these stubs uniformly at random. And I would like to actually show that through a simulation on the network pages. So this is the network pages site. Demos that allow you to demonstrate how such a configuration model is being obtained. So this is one realization. I'm going to be drawing another. What you see is all the vertices, and all the vertices have little sticks coming out, and you pair these little sticks uniformly at random. Then of course you get something which is fairly strange, but it's sometimes called a force field layout. And then you see certain vertices that have a slightly higher degree. Here the maximum degree is 5, and you see that they're vertices you're pairing uniformly at random. You actually have very little to say about how the pairing occurs. And then of course it could be the case that some vertices are a self loop or multiple as sort of small circles. So let's just do this once more, and then you see how the half edges are being paired to one another. It goes pretty quickly, and then in the end, this is what you get. And in this case, it turns out that there are no self loops, but there is one pair of vertices that has a multiple edge between them. So this is what the model is. And here we again have this description, but now in words, where we describe that we're pairing in that respect. Now, of course, the thing that I didn't explain is how one should choose these degrees. And you can have just degrees in the back of your mind. That's perfectly fine. Generally, when we assume that these degrees are somewhat regular. So we want to be able to take a limit as to have a fixed proportion of vertices of a given degree. And that's actually what this signifies. And also what you see here in this second item is that the average degree, so the average of all the degrees in the graph actually converges to the expectation of this limiting degree. So that actually means that there are not too many vertices of too large degree.
Remco, could you perhaps turn off your video? That might increase your bandwidth.
Yes.
Maybe you too as well, Life, although I don't think that's the problem.
I think we don't matter, but we can try.
Yes, I can. Let's see whether that works better. Okay.
Maybe,
yeah. Maybe you can go back. Property, of course, we're interested is that they're generally in the world will basically all connected to one another. So you would believe that the giant component of social relations actually is everything. And in this case, this turns out to be the case when a certain parameter, which we denote by nu, is strictly larger than 1. You can interpret this parameter vertex, loops, and multiple edges. We typically saw only a few of them. The regression model has a random graph. You're very free to choose the particular degrees in your model, the influence of the degree structure on the properties of the network. And let me give a very first example of that. In terms of the graph distances in the network. Distances, no traversal times, but just at shortest GN is the graph distance between a uniformly chosen pair of connected vertices. In this configuration model, different settings. And the first setting is when the degrees have a finite second moment, giant component. And in that case, the graph distances grow logarithmically in n at a certain nu. On the other hand, in the case where there's infinite variance degrees, so tau is in between 2 and 3, this actually means that there are vertices of very large degree, much larger than the square root of the size of the network. And you can imagine that, that such vertices play a very profound role, and in particular that they trace. And it turns out that in such a case, log n. So if n becomes very large, log n is of course a lot smaller, but log n becomes really a lot smaller. So you could see this as a way of quantifying the small world paradigm that we see in real world networks. So times and
Remco,
and there we were interested in both the weight.
Remco, could you just check if there's anything else on your computer open?
I can hear you.
Yeah, anything on your computer open, like the web pages you had? Maybe close those down in case it's trying to transfer data back and forward on your computer.
Yeah, I'll close everything.
Don't close Zoom, of course.
Yeah, I didn't have a lot open. I can close this one. Okay.
Thanks.
Is that better?
Let's see. For now, yes.
Let's see. Yeah, the problem is that I don't hear myself whether I'm coming through or not. It does say that my internet can get to the router. Let's try to do that.
Yeah. I'll press on. It's okay.
And let's see whether that is any better. All right. So I was talking about first passage percolation on the configuration model. And this is the very first result. It's a rather general statement. And the statement says that we're taking these edge weights to be IID, but they have a completely general continuous distribution otherwise. So they could be exponential, they could be uniform, they could be, doesn't really matter. Distribution set here. In this case, we know that the minimum weight to connect, so the traversal time to connect source to destination grows logarithmically with a certain pre-gamma, and actually this turns out to be always the case. On the other hand, if you look at the number of edges in the shortest weight path, this behaves rather differently. And it turns out that if you look at this number of edges, again, this grows logarithmically, but the fluctuations are much larger in the sense that its variance is also logarithmic. So that means that the fluctuations are of size square root of log n. And in fact, there is a central limit theorem there in the background. So the number of edges on the smallest weight path obeys a central limit theorem where the mean grows logarithmically and the variance grows logarithmically as well. And one of the things we see is that these results are completely general, and they depend very little on the precise structure of the degree distribution, nor on the precise structure of the edge weight distribution. So this is what I denote with universality here. And again, this picture for the Hopcount in internet, one of the things we see is that there is a nice central limit theorem in the number of edges of the shortest weight path, just like we see a central limit theorem here in the number of edges in our path. Okay? Now this is of course the case when we assume that the variance of the degree distribution is finite. When it is infinite, and now we're going to be, for the moment, assuming that there are IAD exponential weights, so this is the Markovian setting, then it turns out actually that you can traverse information from source to destination in an amount of time that is tight. So that actually means that if irrespective of how large the network is, in a finite amount of time, you will actually be able to send the information from source to destination, from a uniform source to a uniform destination. While at the same time, there still is a central limit theorem of the number of edges in this path. So that actually means that on the one hand, there are still a lot of edges in the path, but their weight become increasingly smaller in such a way that the total weights along the path, the optimal path, are actually summable. So that's actually quite different and quite rather special as well. So you could say that if we're talking about routing here, that this is super efficient routing. All right. And you can extend that a little bit, that result, by looking at the proportion of vertices that can be reached in a given time. And here it's the proportion of vertices that can be reached at time gamma log n plus some extra parameter t, and that proportion converges to a positive number, and this positive number is in this time t minus some random variable that somehow indicates how quickly the process started flowing away from the source location. And I actually wanted to draw this. So what you should think of is that this epidemic curve is a function that actually goes up like this, and it typically goes up exponentially, then it flattens out, and in the end, it reaches, in this case, the whole population. So this is exactly like the S-curves that we see nowadays for the spread of diseases on these networks. And it's particularly this setting in the beginning, where you have an exponential growth, that is particularly relevant for disease spread. All right. Oh, I want to erase all of that. Okay, so I've described also what happens in the setting where you have exponential traversal times and infinite variance degrees. So there actually the more general results are true in the sense that you have very efficient routing in many of these networks under rather general assumptions, namely that a certain continuous time branching process that we'll say a little bit more about a bit later on is explosive. And that actually means that the continuous time branching process reaches an infinite number of particles in a fixed amount of time. And there is an explicit criterion that will tell you whether such a continuous time branching process is explosive or not in a nice paper by Amini, De Vrooije, Griffiths, and Olver. And it's this sum that needs to be finite. So you take the distribution function of y, you inverse it, and then you take this doubly exponentially decaying function in it. And if this sum is finite, and that's actually going to be true for the majority of H-weight distributions, then actually you have a finite explosion time. Now, of course, that's not always the case. And the simplest example where this is not the case is an example where your H-weight distribution has a minimum of its support that is strictly positive. For example, you could take 1 plus a certain random variable that has a non-negative random variable x. And in this case, it turns out that there's something really weird going on, because it turns out that the minimum number of edges in the optimal path grows exactly in the same way as the graph distances, again log n, even with the same constant. And it turns out that this number is actually tight around this leading order value. So what does this mean? Well, we know that the shortest path is of the same order, again log n divided by this absolute value of log tau minus 2. But now you don't only want to have a path that has few edges, but you also want to have a path for which the sum of the edge weights is actually quite small as well. And it turns out that that is simultaneously possible, to have a path that has both very few edges as well as has a sum of additional edge weights xe that is also very small. That's actually quite nice. And the most complete picture in the case of infinite variance is in a paper by Adriaans and Commiati in JSP, and this is of course not in 2980, it's in 2018. All right, so I would like to devote a little bit of time in my remaining few minutes about the proof. So one of the nice things about the configuration model is that you actually can describe rather closely how the local neighborhoods of such a configuration model behave. So remember that we were starting our infection or our first passage percolation problem from a uniformly chosen source. We denote this by U1, and of course the distribution of this is just going to be the degree of a uniformly chosen vertex, which we denoted by dn. And we've assumed that this is very close in distribution to some limiting random variable capital D. Okay, so now we know how many neighbors a typical source vertex has. But now, what about the number of forward neighbors or further neighbors that any of its neighbors have? Well, how do we construct that? Well, the way how that works in the configuration model is that any of the neighbors of a vertex are obtained by pairing a half edge to a uniformly chosen other half edge. That actually means that a vertex that has many half edges incident to it, and therefore has a very large degree, is more likely to be chosen. And in fact, a vertex that has degree k is k more likely to be chosen compared to a vertex that has degree 1. So that actually means that if you look at the number of forward neighbors of any of the neighbors of my original source location, then the probability that this vertex has another k forward neighbors, well, that first of all means that its degree needs to be k plus 1, because you use up one of the half edges in order to create the edge between the vertex U1 and its neighbor. So its degree needs to be k plus 1. And then, of course, we need to choose a vertex of that degree. And there's so many of those vertices. And then the probability of picking any vertex of them is its number of half edges, which is now k plus 1, divided by the total number of half edges. half edges, which is just the sum of the degrees. Okay, so if we multiply, we see here two sums. If we multiply both sums by 1 over n, our degree conditions are guaranteeing that these fractions actually converge. So the proportion of vertices with degree k plus 1 converges to the probability that my asymptotic degree distribution has value exactly k plus 1. Whereas the average degree, that's actually exactly the same thing as the expectation of dn, will converge to the expectation of d. And what we see on the right-hand side is a nice distribution, and it's sometimes described as being the size bias distribution because we multiply by a value, but in fact it's a size bias distribution minus 1. So the vertex that we attach to has a degree that has a size bias distribution, but of course you lose one of its half edges in creating the edge from the original source. And of course, if we start looking at this random variable in more detail, and if we compute its expectation, then we get exactly this value nu. And remember that nu is larger than 1 was exactly what signifies whether there is a giant component or not in this graph. All right. So what we see is that the forward number of neighbors of U1 are close to being independent, because every time number of half, and you should bear in mind that n is extremely large, and therefore the total number of half edges still present in the system is extremely large. So the very few that are being used up in order to create some of these connections are basically vanishing compared to the large amount. And therefore all of these different forward degree distributions of all the neighbors are close to being IID. But then we can go one level further, and what we see is that the neighbors of the neighbors are again, the number of forward neighbors of the neighbors are again IID samples of the same distribution, which is the size bias distribution minus 1. So that actually means that if you look at these neighborhoods, they look a lot like a branching process. The branching process is a bit peculiar because the root has a different offspring distribution compared to everybody else, but aside from the root, everybody has the same IID offspring distribution, and it's this size bias distribution minus 1. Now, of course, this is the sort of the local neighborhood structure. If we want to understand first passage percolation on such a network, what we need to do is we need to assign edge weights to all of the edges, like we do in the graph. And if the second moment of the degree distribution is finite, it means that our branching process actually has a finite mean. And then we know that these continuous time branching processes actually grow exponentially. And it's also known that if you look at the Hopcount, that's going to be closely related to the central limit theorem for the profile of the generation sizes in a continuous time branching process at a given time. So we can sort of relate the properties that we see in our random graph to properties that we know about continuous time branching processes. Now, when tau is in between 2 and 3, you have infinite variance degrees. That actually means that this B is going to have an infinite expectation. So that means that our branching process, which has this size bias distribution, now has an infinite mean. And infinite mean branching processes are very special. And in such infinite mean branching processes, we have that the continuous time branching process can actually be explosive, meaning that the continuous time branching process reaches an infinite number of vertices in a finite amount of time. And if this doesn't occur, we call it the conservative. All right. So what is now the central ingredient in the whole proof? Well, first of all, what we have tried to do is to untangle the relationship between network topology, here described by the degree distribution, and the behavior of a process on it, in this case, first passage percolation. And what we see is that this high amount of heterogeneity that we see in many real-world networks, also in the random graph, plays a very particular role, and infinite variance degrees have different behavior than finite variance degrees. Now, of course, you may wonder whether sort of these insights can be used in the real world. Well, you have to be really careful for that, and the reason for that is that the configuration model is in many respects not such a good model for the real world. The reason is that many real world networks actually have a high amount of sort of small cliques and triangles and so on. And that's what you generally do not see in the configuration model. but still many of the results that we're seeing in the configuration model actually hold much more generally. And the configuration model certainly serves as a nice sort of example model and can be used as a stepping stone for other results to be proved. Now, of course, an open problem and a much more difficult problem would be to investigate settings where the edge weights are actually dependent random variables. And then it's not so clear how robust the results are with respect to these dependencies. Now, first passage percolation can also be seen as a model for the spread of the disease, and then it would be called an SI model, susceptible infective. And this is a model in which anybody who's infected will remain being infectious all the time. Now, that's of course not a very realistic model for the spread of a virus, because in viruses you generally have a contagious period that is only finite. But actually, you can combine results for first passage percolation together with results for ordinary, to also say some for the spread of diseases. And a few of the important names are Frank Boll, David Searle, Peter Trapman, and many others also in France. Looking back at the pictures that we've seen, I've been arguing that infinite variance degrees are very relevant for many of the real world, let's say, electronic networks, but they may actually not be so relevant for or realistic for the spread of proper diseases. And the reason is that, for example, in the coronavirus, what we see is that initially things grow exponentially. And that's not something that goes very well together with the explosive nature of what we see in general in infinite variance degree configuration models. So apparently, if we look at social networks, this exponential growth is much more relevant there. Now, there are many more open problems. I don't have a lot of time left. So let me go to the conclusions. A few conclusions about networks. Many real-world networks share important features. They tend to be scale-free and they tend to be small worlds. There's often a suggestion of infinite variance degrees, particularly in many of the electronic networks, such as the World Wide Web and Internet. And there's many models invented to model or explain these properties. And here in my talk, I focused on the configuration model, but there are many more other models out there that sort of take different aspects of such real-world networks into account. And what we see about these weighted distances is that they're remarkably similar across models. This is something that we haven't really discussed, but one of the things that we have seen is that sort of in the finite variance regime, actually this first passage percolation behavior is remarkably similar across different edge weight distributions or degree distributions. And we see that also when applying these ideas to other random graph models. And there is, of course, a main difference. When you have infinite variance degrees, you can have explosive settings, whereas you have exponential growth or exponential growth of the spread. All right, that was it. Let me try to start my video.
Yeah, thank you very much, Remco.
Again.
This was now a little bit unlucky, but we knew it's going to happen sometime that the internet connection is not good enough. I saw questions in the chat. So everybody has the possibility to unmute as before. Do you want to go forward asking the question live? So I'm going to start just from the chat. Christina asked if it would be a natural, what would be a natural dependence structure for the edge weights?
Oh, that's an excellent question. I don't know. And I think that there's very little data on that. So that actually makes the question difficult. So maybe, you know, if you think about the model as being a model for the spread of a disease, maybe then you can think a little bit more about this. So for example, you might have people who are socially very active, and I can imagine that they reach all of their neighbors more quickly than people who are less socially active, right? So then it would mean that in general, the distribution of edges, let's say outgoing edges from a certain source, might be dependent on the precise properties of the source node they start from. So you could think about settings where you let the dependency occur through the vertices from which the edges come. Does that answer the question?
I think so. Christina says, thank you.
Can I ask a slight follow-up to that?
Yep, sure.
So, I mean, you sort of mentioned that in a way, there's lack of cliques or sort of small groups is what's missing from the configuration model.
Yep.
On the other hand, physical models where we understand local dependency, I'm thinking things like easing model are well studied. Is there some way of imposing some sort of geometry on the network so you have sort of locally a sort of easing model, but with these long range independent links as well? So
I'm thinking more about a setting in which a model can have lots of little triangles. So vertices are part of a large collection of triangles and maybe even larger cliques. So I don't really see the connection to an easing model there. But of course, you can try to put that into your random graph model. And then the question, of course, becomes whether, let's say, the kind of properties that we currently see in the configuration model, whether they still remain on being true in such a setting where you have much more cliquish-like behavior, while at the same time keeping an average degree that is not too large, right? Mm-hmm. Does that answer your question, Amanda?
I mean, I think, yeah, it was a crazy suggestion, so don't worry about it.
I would have to think about how to do that using an easing model.
So I see a blue hand raised, Patanier, so I'm going to unmute you.
Oh, now. Hi. Thank you. Remco, this is Parthanil from Bangalore.
Ah, yes.
Yeah, thanks for very nice
hearing you, Parthanil.
Yeah, so my question was, you said that dependence among the edge weights is sort of normal, perhaps, to assume. But is there any literature on that? Like what kind of dependence would you model? Or is it long range, short range? Would you expect same result?
I have no idea. I don't know of any literature. That's for one. In fact, it's not entirely obvious in what setting you could actually measure these kind of things.
Yeah.
So for example, in internet, in principle, you might be able to do this, but I don't know whether there's any data sets out there that will tell you.
Okay. And nor is there any theoretical result, as you said.
No, not as far as I'm aware. I can imagine that, you know, there's lots of people trying to model disease spreads. So I can imagine that there's a lot of data on that, sort of what the variability is of people when they're infected, how they spread the disease to their neighbors. And I can imagine that is highly heterogeneous and depends strongly on the person. And that would create a particular dependent structure in the traversal times along the edges.
Yeah, of course.
But again, I don't know of data there, but I would be surprised if that doesn't exist.
Okay, thank you.
If anybody in the audience has to contribute to this question, just raise your hand quickly and I could unmute you as well. So I think we don't have further questions in the chat. So as before, I'm going to unmute all of you so that Remco and Amanda again can collect their well-deserved applause of all of us. So I think 1, 2, 3. Everybody should. wonderful presentations. For today, you're still interested to discuss with anybody in the chat, although it's the speakers, just go ahead and we'll see you next week.